Hi and welcome. Let's continue our discussion with the multi-level inverters. Today's topic is the cascaded edge bridge converter. If we have applications that require higher voltage and reduced amount of harmonic contents, then this is often the chosen application of converters for that purposes. As you can see here, I have shown you a very generalized schematic view of the cascaded edge bridges. So this is for a three-phase applications. You see there are three half bridges that are connected in series in each phase. Now inside each edge bridge we have 4 IGBT switches and a DC source here. And if we connect them in series or in cascaded manner, the output voltage of the leg would be the summation of each individual leg voltages. For this demonstration purpose, I have shown you here 4 submodules here, even though here in the 3 are shown, but as I said, these are just generalized representation. And you see the connection on the AC leg are then shown here for the series connection. There are different types of modulation schemes depending on the chosen application. Could be the phase shifted PWM or level shifted PWM. These are the two mostly used schematics, mostly used PWM scheme. And today I'm going to discuss that level shifted pulse width modulation. Now, what is that pulse shifted modulation? I've directly shown you the curves from the simulation for better representation. You see there are 4 triangular waves or carrier waves. Now I will explain you later why 4 here, why not 6 or 8 or some other number. That will be clear in an instant. Let's carry on with the 4 carrier waves at this moment. So level shifted carriers means that in this pulse width modulation, if we want to generate our reference waveform, which are the sine waves in this case, we compare this reference wave against the level shifted carrier waves. Now, this number of carriers can be calculated depending on how much level of the voltage we want to have in our output of inverter. I'll come to you later for the calculation of number of these, but the switching logic is produced depending on the comparison of this reference wave to the carrier waves. Now, for the simulation purpose today, I will consider 2 edge bridges that are connected in cascade, and that will ultimately give us 5 levels in the voltage, output voltage. So if we want to calculate the switching PWMs for bridge H1 and H2, so these are the logics. If we consider the reference voltage with triangular waveform 1, then S1 is 1, S2 is 2, S2 is 0. I apologize. So these two are then complementary. And then in the second phase, we compare the reference wave to the third triangular wave. And in that case, if this is true, S4 is equal to 1 and S2 is equal to 0. So this is important at this point. For bridge 1, we need to consider the triangular waves that are adjacent to the 0 axis here. You see, I have shown you this axis. So here is the 0, and it goes toward the positive y direction until 1, and to the negative y direction until negative 1. So for the half bridge, the H bridge H1, we need to consider these 2 carriers which are adjacent to the 0 axis. And for second bridge, we need to consider the uppermost and the lowermost, for this particular case, carrier waves if we have, for example, more than 4, like 6 carrier waves, in that case we need to continue in a similar fashion. That means if we had one on the top and one on the bottom, then we need to choose the topmost and the bottommost carriers for bridge 3 if we had. So you see I have named is triangular 1 and 3 that are adjacent to the 0 axis. The naming is completely up to you. The important is that we consider that adjacent to the 0 axis. So for half bridge 1, this is triangular 1 and 3. Not half bridge, I always mix it up. This is an H bridge. And for H bridge 2, then we have triangular 2 and 4. That is the farther pair of carrier waves. And here is the relevant switching logic for that. I already have built up the simulation model so that we can gain some time. So on the top I have some parameters for the IGBTs, and for the PWM generation, this is quite important. Let's go through each part in details. I consider a switching frequency of 2 kHz at this point. We can change it later if need be. And I take the reference wave of sine, the amplitude to be 1. As I said, we have the number of cells, which is the number of H bridges is 2. So if this is the case, if we have 2 H bridges, then the number of levels on the output voltage is going to be 2n plus 1, which is 5 in this particular case. Now to calculate the carriers that we need to use in the PWM generation, we need to consider the level and subtract 1 from that, which is this case here. So number of carrier is equal to number of level negative 1, which is 4. And this is the reason you saw here in that PWM generation, 4 carriers. And of course, level shifted. The amount of shift I will also discuss right away here. So the carrier, a carrier is the amplitude of the carrier wave, and this is if we have the reference, which is maximum value, to 1 to keep the linear modulation. It's 1 divided by number of carrier. That gives us the amplitude of the carrier waves, which is 0.25 in this case. And for the implementation in MATLAB function, I also take an auxiliary variable, a carrier peak to peak, which is the double of the carrier waveform. This particular line is quite important, this particular section I mean, and this calculates exactly how our shift in the carrier wave should look like. That means this determines the vertical shifts of the carrier waves. So this is just initialization to 0 vectors, and the amount of level, that means how far it is from the 0 level or the 0 axis, as I mentioned before, is determined using this level. So I take the ceiling function I minus 1 by 2. This gives us the distance of the vertical distance of the wave relative to the 0 axis. Now remember, we have an alternating pattern of the carrier waves. That means if I take triangular wave 1 here, then we need to immediately switch back to the alternating waveform, which is triangular 3. So if we go 1 for the positive direction, the second goes to the negative direction. And again, for the second pair of carrier waves, which are triangle 2 and tri 4 here, we have one going upward, that is in the positive direction, and another going downwards, which is in the negative direction. And for these alternating waves, I have taken a sign that alternates between plus and minus, and ultimately the shift of the carriers is then found by multiplying the sign factor to the level and also the carrier peak to peak. Let me show you. If we do so, I have already commented out my power circuit just to show you inside here. So this function here, particular function in MATLAB, generates the carrier waves, and also the sine, which is our reference wave, is also shown in this case. So let's see how it looks like. So these are the 4 carrier waves, and red one is the sinusoidal waves, which is the reference wave. Now, of course, you could have taken 4 different triangular waves as repeated sequence, as what was the name here? In Simulink, I mean, it is a repeating sequence. But if you now you can clearly see for 4 carrier waves, we need to take 4 of them, and individually we have to adjust the parameters for that. I wanted to avoid this type of hassle, and that's why I chose to do it programmatically. In that way, if you have just the specification of the number of cells, you can have the corresponding number of carrier waves with exactly the amount of amplitude and the level shifts. Now, for example, instead of 4, you want to have like 5 cells, for example, which will give us 10 level inverter operation. Let's check the value. You see, in a matter of instants, it's already created these 10 carrier waves for us. And this program automatically determines what should be the amplitude of the carrier waves and how should be the shift level vertically, and also positive vertical direction, negative vertical direction. Both are automatically adjusted. So you can go crazy. You can say, okay, I want 10 number of cells, and see if it produces exactly that number of carrier waves, which should be 41 in this case. It's too much, I think. Yes, but you see these are perfectly generated. So you have, this is, I have also done maybe in later video tutorials. I want to do even more level of voltage generation, but let's go back to our original set here, 2, and rerun again. So here we have the original PWM generation. So this part of the function is now for the generation of triangular waves. As you see, I have specified here the amplitude. Let me show you what the function looks like. I say this function should generate a variable called V triangular. That means the triangular voltage, our carrier waves. And it takes as input the time that I specify in the Simulink environment, the amplitude that I already calculated here is a carrier, this one. Fc is the carrier frequency, which is specified here, F tri, and the shift. Now these are all taken as a shift is taken as a vector here. You see, according to the number of cells, the shift carrier variable is a vector as a result. And here is the initialization again. The first values are 0, and this ultimately calculates that level shifted carrier waves as we saw earlier. Now this particular case I have created for phase A. I wanted to keep things quite clean so that I also can follow. And inside the PWM generation, if you remember, we need to have our carrier waves and the sinusoidal wave, which is, again, let's see it here. So we have to compare this reference wave to our carrier waves, and depending on where we are, we produce the gate signals of the IGBTs accordingly. And this is done exactly here. So it takes, for example, a sine, which is the wave that we specified in Simulink, and Vtri is triangular, then is the vector of all triangular waves generated before. You could also take sine as a variable, like 120 degrees phase shifted, but in that case, at least for me, the code gets too complicated and it's not so easy to follow. That's why I separated for each phase the codes, and for a cleaner implementation. So you see from the code I get the PWM for bridge number 1 and PWM for bridge number 2. And inside comes our switching logics. So if we set the reference voltage, now before that here is just the implementation to 0 or initialization. And here you can see if we have the sine amplitude greater than the first triangle, then we have switch S1 is equal to 1, and S2 will be then complemented, which is shown here. For bridge 1, the switch S2 is the complemented one, since they are in the same leg. To prevent any shoot-through or the short-circuiting of the DC link, we have to complement the signals. Since I'm still considering an ideal converter, I didn't consider any dead time yet. Maybe later, but let's continue with the ideal discussion. The switching logic, let's have a look again. So this is for H1, the bridge H1. I compare with triangle 1, which we just saw. In the second case, we compare to triangular wave 3, which is exactly seen here. So if sine is greater than triangular 3, we have S4 is equal to 1. And if S4 is equal to 1, S3 is the complement of it. Now it continues similarly with the PWM generation for bridge number 2. And similarly, also here the complement of the switches. Now to give the output as a vector, I group them here for PWM H1. That means it will give me the vector of 4 elements for bridge 1 and similarly 4 elements for H2. If we come out of the blocks and let's activate now here our power circuit. Let's go inside. And you see we have 2 H bridges in phase A and similar for B and C. So inside each H bridge, you see we have the 2 legs with 2 IGBTs each. So 1 and 2. I have named it accordingly. This is extremely important that you name it before and follow your logic accordingly. So in the same leg, I have 2 IGBTs 1 and 2, and the second one 3 and 4. Once we determine the pulse width modulation signal for IGBT 1, I can just take the complement of it to get the gating of IGBT 2. And same for the second leg as well. You see, I've imported the PWM and connected them to the relevant switches. 1, 2, 3, 4 as come from top to bottom, 1, 2, 3, 4. And this is applicable to all other bridges. So this gives us the more of a modular workflow of the simulation. And also it reduces the amount of work. And then each phase is then connected to our, this could be the representation, it could be load, machines or grid or anything. Since I don't have a particular application here, I have pretty much generalized everything, and the target is also just to see how to implement it at all. And you see the generated pulse width modulations are then separated for each individual bridges here. So this is phase A H1, phase A H2. For phase A in general, we have two input signals that we take from the Simulink, and also same for phase B and C. So if you go here, as I said, you could have taken only one block here and generate for all three phases all the signals here, but since this is a messy situation in that case, I decided to separate for each phase. So here the only difference is that we have the phase shift of the sign to be 0 here, and for B it's exactly the same codes, same blocks, even the namings are the same. Why is it different here? Okay, this is very funny. I didn't change it. Okay, let's do it together. Here you see I have generated the triangular waves using this block, I mean with a programmatic approach. And here I had, from my previous simulation, I had to go each time into the repeating sequence to adjust the level and the amplitude of the carrier waves, which is a whole lot of work. And this is the reason I switched back to the programmatic approach. So what we can do, simply delete this, and same here. I would say copy this, and again for phase C. The only thing that we need to change is this one here. We need to add a phase shift of 2 pi by 3, which is 120 degrees. And let's get out of it. Do it for phase C. And in that case, it should be minus 4 pi by 3. This is a mistake, so it should be all lowercase letters, pi by 3. So now here we have, with these three blocks, we have implemented the level shift PWM. And for phase A, I said there are two bridges, so I have taken here two go-to blocks, each containing 4 signals, since they're in full bridge, and they're imported here using a from block. So I feed the values to the PLECS environment. And here is again the input or import of in the PLECS environment. So if we go to the settings of M file again, so here, this is the discussion. Let's continue here. So this was to generate the PWM carrier waves, PWM signals. And as I also mentioned, that since this is a very generalized model, for the load I take 1 ohm and 1 millihenries respectively. Simulation time is 200 milliseconds. And this is very, very important. So depending on the switching frequencies, for the accurate calculations, we need to have at the reduced amount of time step. Otherwise, you will see there the values of the triangular wave, the peaks are clipped. Sometimes you don't get enough accuracy for your calculations. So as a rule of thumb, if you have the switching frequency, F try and then just take a multiplication within the 100, that gives you even smaller time step than the time period of the switching frequency. And for refine factor, I just took to 3. Let me show you what these values are. So I have taken a discrete state space, and maximum time I have taken 1 millisecond, and refine factor is specified here. And in the Simulink simulation setups, we have the solver settings here. I have taken a Steve NDF solver. if everything is fine, it should run without any problems. You can forget these values. I mean, DC link voltage is important. For our case, I have taken here 500 volts, and these are the some IGBT parameters. As I said, we have ideal switches here, but these are just a little bit addition to their properties for more practicality. Let's run it. So let's check our, yes, these are 4 carrier waves with the sine waveform, and we should go to the PLECS environment. So you see, for the measurement here, I have taken individual H-bridge voltage measurement and also the summation of them. These are then shown in the top oscilloscope. So these are the results. You can see when the H-bridge 1 is switching, I mean, it's a summation of both of them. So top one is the output voltage of H-bridge 1, second is for the second H-bridge, and third one is the leg voltage, which gives us, then you see there are 1, 2, 3, 4, 5 levels. Since we have 2 cells or H-bridge, it gives 2n plus 1, that means 5 levels in the output voltage of the leg, which is exactly here. You can see in the third window. And this is important actually. Look, see, we will discuss it later, but as a quick reminder, you see in the H-bridge, the switches are on for a longer time, while the switches on the second bridge is switching continuously in that range. So the conduction and switching losses in both bridges will be different, of course, and maybe a rotational switching pattern would be required to choose for a better distribution of losses of the IGBT switches. But more on that later, not today. Here is just the discussion on how we can implement it. Let's continue with our measurement here. So I have taken the line-to-line voltages, the load voltages here, and also the line current, which is shown in the second oscilloscope. Okay, why we don't have this? Maybe the measurements are not yet there. So this one, yeah, this is the voltmeter is missing. Let's take the load voltage here. Measured voltage for the second one. Let's take the line-to-line voltage. And third one, let's take the current. I will take the current of phase A. Let's take resistor, and then the resistor current is the phase current ultimately. And this is already there. This is again the leg voltage I wanted to show here. I think I need to excuse me. So it is rerun now. So now we can see that one as well. So first one is the load voltage here. Second is the line-to-line voltage. Third is the current, line current. You see it's almost perfectly sinusoidal. And we have the load voltage down here to the fourth window. Now you can play around with the switching frequencies, like you can take, instead of 2, let's do 20 kilohertz, run the simulation and check. You have even less harmonics here. It's straight away, it's very clear. Let's wait a little more until it's finished. And you see the sine wave is very pure sine wave here. So as I said, in your application, the requirements could be different, but for this tutorial, we have considered these working conditions, which must be adjusted for a particular application. Now, in the future, part of the discussion, we'll consider the frequency analysis of the waveforms, like if the harmonics are reduced, what type of advantages we have then, and other implementations like phase shifting of them, or maybe closed loop control of that, and many more things. I think for today I have covered everything I wanted to discuss, but if you have questions, please let me know. I'll try my best to answer. And until then, thank you for watching.